Hello! In this short lecture, we'll look closely at the parallel and perpendicular vectors. We will aim at finding the mathematical solutions for the following problems. For any two vectors, how to test whether they are parallel. For the given vector, how to find more vectors that are parallel to it. And perhaps I don't need to tell you this, but parallel vectors are the vectors that extend in the same direction, so they never converge or intersect. Moving on. For any two vectors, how to test whether they are perpendicular, and for the given vector, how to find more vectors that are perpendicular to it. And the perpendicular are vectors which not only intersect, but do so at the right angle of 90 degrees or pi over 2 radians. By the way, we consider the angle between the two parallel vectors as 0. This lecture contains some calculations which you should follow at least once, but they are not essential if you are reviewing this material. In that case, you can consider jumping straight to the take-home message section, which should be linked in the description below or above this video. So, when two vectors are parallel? Well, the simple answer is when the direction is the same. Last week we have considered vectors as mathematical entities which have a magnitude, also known as the length, and the direction. Whilst the magnitude is easy to find from the Pythagorean, the direction is often identified as the normalized vector, sometimes called the direction vector, or even the normalized direction vector. This is the vector that maintains the same direction as the original vector, but its magnitude is scaled down, or maybe up, to 1. Mathematically, the normalized vector can be found from the division of the vector by its own magnitude, as shown in the formula. So, if we compare the normalized direction for the vector v and the normalized direction for the vector u, if the vectors are parallel, the normalized directions should be equal. So, let's take the first coordinate x of the direction vector of v, which is the x-coordinate of the vector v, or xv, divided by the magnitude of the vector v. And this should be equal to the x-coordinate of the vector u, divided by the magnitude of the vector u. We have now the first condition testing if the vectors v and u are parallel. But this formula can be simplified. First, let's get rid of the square roots. If these two expressions are to be equal, then their squares must be equal too. So, xv squared divided by xv squared plus yv squared must be equal to xu squared divided by xu squared plus yu squared. So far, so good. Now, let's get rid of the fractions by multiplying the numerator on the left with the denominator on the right, equal to the right numerator multiplied by the left denominator. Now, let's remove the brackets by multiplying the xv squared by xu squared plus yu squared, and similarly the xu squared by xv squared plus yv squared. Now we can find like terms. Here is xv squared here and here, multiplied by xu squared here and here. These two terms are identical, therefore cancel themselves, and we get a significantly simpler equation now. Xv squared times yu squared equals xu squared times yv squared. If the squares are equal, then the values under the squares must be equal too. So xv yu equals to yv xu. And one more step, moving both terms to one side, we get this final formula: xv times yu minus yv times xu equals to 0. Why is this formula so special? Well, Last time, when we discussed the multiplication of vectors, I presented what we called the fast formulas for the vector multiplication, the dot and the cross product. These were these formulas. Apparently, what we have just found is the cross product of vectors, so finally we can replace our condition with the following. Vectors v and u are parallel if their cross product is equal to 0. So, the first part of our take-home message is if you want to test two vectors, whether they are parallel, take their cross product, compare it to 0, and if equal to 0, then the vectors are parallel. But what if you tell me, I don't like your normal vectors so much, and if I was to test two vector directions, I would rather take the direction angles or gradients. Yeah. Well, here you are. These angles, here shown as alpha, are easy to find from trigonometry, and to be more precise, the third part of the SOHCAHTOA, which is tangent. So, from the larger triangle, this one, we get the tangent alpha equal to the opposite, the y coordinate of the u vector, which is yu, over the adjacent, the x coordinate of the u vector, so xu. And from the smaller triangle, we get yv over xv. As the two angles must be the same, we can now write an equation like this one. And now multiply the numerator here by the denominator here, and the numerator here by denominator here, and we get something like that. Now moving both terms to one side, we get the same formula as previously, but faster. This is the same condition for the cross product equal to 0. Wow, you were right. In this case, working with angles and the SOHCAHTOA was faster to arrive to the final formula. But the important point here is, whichever method you choose, you arrive to the same result. Consistency is the beauty of mathematics. One more approach. If one vector is parallel to another one, it has to be possible to obtain it by multiplying this vector by a number. Multiplication of a vector by a number scales this vector up or down, or so can change the vector magnitude or length, but cannot change the vector's direction. So it is a good candidate for another test for parallel vectors. Will it, as the previous two, lead to the same result, the cross product equal to 0? Certainly it has to. So if the vector u is the vector v multiplied by n, then each of the coordinates xu and yu must be multiples of the xv and yv respectively. Now rearranging the equations so that to have n on the left in both equations, and equating the right sides, let's get rid of the fractions, final rearrangement, and yes, this is the same equation once again. It was fast, I know, but we've done similar examples twice before, so maybe I will just leave you a second to press the pause button and analyze the maths in your own pace. Okay, well, I used this multiplication by number formula not just to demo one more method of finding out when vectors are parallel, but because this particular formula is very useful for something else, and this is how to find vectors parallel to the given one. If for the given vector xy we'll find any other vector that fits to this formula nx and y, then this vector must be parallel to the given one. N is any number except of 0, because 0 would produce a zero-length vector, and a zero-length vector has no direction, therefore being parallel or perpendicular is not applicable. So, for an example vector 4, -5, one of the possible parallel vectors with n equal 2 is 8, -10. Or another example for n equal 4, 16, -20. But n can also be less than 1, so another example is 1, so the n value is now not 0.25, and the second, the y coordinate, will be -1.25. But we can also have a parallel vector like this one, -4, 5. This is of course the case of n equal to -1. So what happens if the n number is the negative number? Of course, what we have is the inverse vector, -x, -y. Apart from the obvious example of -4, 5, another inverse direction parallel vector for value of n equal to -2 is this one, -8, 10. The next topic discussed today must be the perpendicular vectors. This time we will immediately deduce the test formula by an analogy, or rather by an educated guess. If vectors are parallel when their cross product is 0, then it's reasonable to think that they are perpendicular when the dot product is 0. And this guess is very well justified. The cross product used to test parallel vectors by the power of its definition formula is attached to the sine of angle. The angle between the parallel vectors is 0, and the sine of 0 is 0. Therefore, the cross product is 0 as well. In case of perpendicular vectors, the dot product is attached to cosine of an angle, and this is the cosine of 90 degrees of the right angle, that is 0, and this is the angle between the perpendicular vectors. So, two vectors are perpendicular if the dot product is equal to 0. Here are, as a refresher, the formulas for quick calculation of the dot and cross product. I called them last time the magical carpet because each of them provides very useful and trigonometry dependent values, but only each of them requires 2 multiplications and either an addition or subtraction to calculate. So now, using the quick formula for the dot product, we can do this simple calculation, which I will only briefly comment. So we start with the quick formula for the dot product equals to 0. Then simple rearrangement by moving this term to the right side. The next step is to divide both sides by the expression xvyv to get the fraction form of the equation. In this equation, there are like terms here and here, xv and xv in the numerator and denominator. They will cancel themselves, and also yv and yv here will also cancel themselves, giving us a much simplified form of this equation shown here. At this point we introduce additional number n, which is proportion between these terms here, and we break down this equation into two equations, equation number 1, equation number 2. From equation number 1 we get the final formula for xu, and for the second equation we get the formula for yu. Now please note that this xu and yu are the coordinates of the vector which is perpendicular to the vector xv, yv. In other words, we have just found a recipe for the perpendicular vectors, and this is ny negative nx. This closes all the topics prepared for this lecture today. Just let's have a few practical calculations for perpendicular vectors, and we will be moving on to the take-home messages. So let's take, for example, the same vector as previously, 4, negative 5. Now, the basic perpendicular vector will be a vector with n equal 1. So the first coordinate will be ny. So we are just copying the y coordinate of the previous vector, and minus nx. So it's negative 4. So it's 4 with minus. Here. That's a vector which is perpendicular to this one, and of course we can multiply these values, so every parallel vector to this perpendicular vector will also be perpendicular vector. So for example, negative 10, negative 8, but also a vector like 5, 4 will be perpendicular to this first original vector, and this is why this is because we have used the value of n equal minus 1. So now ny is minus y, so minus y is negative 5, double negatives produces a plus, so we have 5, and then we have 4. Basically, you can notice that to get a perpendicular vector, particularly this one here and this one here, you have to swap the coordinates, x with y and y with x, and then flip one of the signs, because you can use either positive n or negative n. It doesn't matter which one you flip, one of them has to be flipped. So let's do the final example. 2.52 will also be perpendicular to this initial vector 4 minus 5. It is time now for take-home messages. If you have two vectors v and u, and you need to test if these vectors are parallel, then find their cross product, and if the value of the cross product is equal to 0, the vectors are parallel. If you have these vectors and you need to test whether they are perpendicular, find the dot product value, and if it is 0, then they are perpendicular. If you have a given vector with coordinates x, y, and need to find a vector which is parallel to it, anything that fits to the pattern nx, ny will be parallel. So basically you have to multiply both x and y by the same number. And if you have a given vector with coordinates x, y, and need to find a vector which is perpendicular to it, then anything fitting to this template ny minus nx will be perpendicular. So this means that you need to swap the values of x and y, then flip any of them, either x or y, to an inverse number, and you can also multiply both x and y by the same number. So thank you very much for watching. Please don't forget to watch the practice video, link to which should display somewhere here, as well as the next lecture, which will be about solving triangles with vector algebra. Thank you very much, and goodbye.